All right, everyone, we're on to section 9.4. 9.4 is titled Improper Integrals. We're going to go back to integration. But this is integration, be a little bit trickier. It's going to all be definite integrals, first of all. It's going to have limits. So not only are we finding antiderivatives, but it's going to turn out that all of these integrals are called improper integrals because there's going to be some sort of infinity in them. So I'm just going to explain what they are generally and then do some examples. So the first most common type probably of improper integral is just one when you're integrating from some number to infinity. Okay. So it seems funny. It's just an infinity up there instead of a number. So what we're going to do is very simply is we're going to just call that infinity a t. You can call it any variable you want. We're going to call it a t. And then we're just going to take that integral. We're going to plug in the t. We're going to plug in the number, the a, whatever it is. Do an antiderivative like we normally would, subtract, but then we're going to do a limit as t approaches infinity, okay? Because infinity is not really a number, so we just turn it into a limit, basically. It's possible we might get some L'Hopital's rules and things like that. You could get infinities over infinities or infinity minus infinity in these. That's the first type. The first set are all pretty similar. The next one is just if you're starting at a negative infinity to a, it's the same thing. You're going to plug in a t for that infinity, and then take the limit as t approaches negative infinity in this case. And I'll do a couple examples here. It'll probably make sense. And the third one, which is the more complicated one, is the one when you're going from negative infinity to infinity. If you're going from negative infinity to infinity, what you got to do is break it up into two integrals. So you can break it up wherever you want. Notice in this particular case, I just broke it up at a. But you can break it up wherever you want. Could be any number. Typically we use 0. It's just the easiest because plugging in 0 is pretty simple. And then you have to do limits on both sides. And what we're doing is this. Let me draw you a quick little picture. If we're like integrating this curve from 1 to infinity, remember that the integral is just area under the curve. So let's just call this f for here. And we go 1 to infinity. We're finding this area. It is possible that area could be infinite area. It could be. It looks like it is, right? Because it's going to infinity. But if that graph is approaching that x-axis pretty quickly, there's actually going to be a limit. It's actually not going to go to infinity. Maybe it stops at 23 or something like that. We're going to study these sorts of limits in depth in our last chapter in this course, in our series chapter. But for now, we're just going to see how they show up in the integration. So let me erase this. I'll do a couple examples for you. And then there's another type of indefinite integral also. So dx over x from 1 to infinity. So again, remember what we're going to do is we're going to take the limit as t approaches infinity. And we're just going to put a t in for that infinity. And now we're just going to go through our regular process. So this is just 1 over x. The integral of 1 over x, you hopefully remember, is the natural log of x. So this becomes the natural log of x. So we wind up with the limit as t approaches infinity of the natural log of x. We're going to integrate that from 1 to t. And we get limit as t approaches infinity of the natural log of t minus the natural log of 1. Now it's just a limit problem. This is the reason we just did L'Hopital's and reviewed limits. So this natural log of infinity is infinity. The natural log of 1 is just 0. So in this case, it is an infinite amount of area. Okay. Sometimes it will be, sometimes it won't be. Here's another example. So first thing again, limit as t approaches infinity, 1 to t of 1 over 1 plus x squared. Going to get some practice in integration again. 1 over 1 plus x squared is a tangent inverse. Hopefully you remember that one. Limit as t approaches infinity of tangent inverse of t from 1 to tangent inverse of x, from 1 to t. So we're going to go limit as t approaches infinity, tangent inverse of t minus tangent inverse of 1. You plug in that infinity. You may remember we've done this before. The tangent inverse graph looks like this. It's been a while, I know. We had a little vacation. Looks like this. So as we approach infinity, the tangent inverse actually approaches pi over 2. And then the tangent inverse of 1 is pi over 4. We subtract those two, and we get pi over 4. So in this case, there was an area under there, and it was pi over 4. So that's the first type of indefinite integral. or called improper integral. It's also indefinite because it goes infinity. It's just the one where we have infinities on our endpoints. It's just, you're just going to have to do antiderivative. There's nothing too tricky, but you might have to do some u subs, you might have to do some stuff like that, and then do a limit after that. Those are the most obvious or easiest types of improper integrals. The harder ones are the next ones because you see that infinity in there. However, the next form is what's called a discontinuity in your integral. So when there's an asymptote in your integral, a lot harder to recognize these. So for instance, let me just give you an example here. If I was integrating 1 over x, let's go back to that same one. There's an asymptote at 0, right? We actually did this one 2 minutes ago. It was from 1 to infinity, so my asymptote didn't matter. But if I did this, I'd have a problem, right? Because there's an asymptote at 0, so I would have to deal with that asymptote. This is going to make your life, honestly, a little bit harder on integration, because normally when you have limits, I'll just take the antiderivative, we'll plug in the numbers. But if there's an integral or an asymptote in the middle of it, it doesn't work, because what happens is this, right? Okay, so you have some possible infinite error. It might not be infinite, but it could be, again, same thing as it was in the last problem. So what we're going to do is we're going to break every integral up that has an asymptote into 2 different integrals. So in this case, the asymptote's actually on the endpoint. So notice I have an open parentheses on A and a closed bracket on B. So that means there's an asymptote at A. All right. So notice what I did was I replaced that A with a T, again, just like I did with infinity. And then I'm going to do a limit as T approaches A from the right side. And I'll do some examples of these to make a little bit of sense. The next one is if that asymptote's on the right-hand side of the integral. Then what we're going to do is we're going to plug that T in for B in this case, and then take the limit as T approaches B from the left side. And for reason from this left side or the right side in the first one, left side in the second one, it's just because that's the side of the integral we're in. And the third one is the example I just showed you. If the discontinuity is somewhere in the middle, right? If it's somewhere in the middle, we have to break it up into 2 integrals. So let's say the discontinuity is at C. We're going to go from A to C, and then we're going to go from C to B, and then we're going to do 2 different limits. Okay. So I got a couple different examples. So let's start with this one here. I'll come down here and rewrite it so you guys can see it better. We're going to go 0 to 3 of 1 over the square root of 3 minus x. And let me just throw a couple of words at you here before I go on. Converge and diverge. Sometimes they'll just ask you, does it converge or diverge? Diverge is basically the same thing as infinity. So the integral diverges if it goes to infinity, and converges if there is a sum or an answer, right? If there's some sum of that area, we just say it converges to, so we might say like it converges to 23 or the whatever the number is. Remember that area is not exactly that area because we're taking a limit, so it's getting closer and closer and closer. You might remember these terms from Algebra 2 honors. We're going to study these terms again last chapter. Converging, if a limit converges, it converges to a number. If it diverges, it goes to infinity. So what we're going to do here, notice there's an asymptote at 3. Okay, so what we're going to do is we're going to plug in a T for my 3, just like I did in those last sets of problems. And we're going to go 3 from the left side because we're between 0 and 3, right? So whatever my picture looks like, we're going from 0 to 3, and it's all in here, right? So we're approaching 3 from the left side. Now we're going to do the integral. I'm going to do u sub here, u equals 3 minus x, which means du is negative dx, so I get a negative sign. I'm going to ignore the limit and the t's for just a second until I'm done, if that's all right with everyone. So I'm going to get a negative sign, and then it's going to be u to the negative 1/2. And then I integrate u to the negative 1/2. I get u to the 1/2 over 1/2, or times 2. So negative 2 u to the 1/2. And then when I plug back in, I get 2 times square root of 3 minus x. Now I'm ready for my limits and all that. So we'll go back to 0 to t. Limit as t approaches 3 from the left side. Now we got some more limit practice. So here we go. We're going to plug in now. I'm going to factor out that 2. So we're going to get square root of 3 minus t minus square root of 3 minus 0. Now this 3 is going in there, right? From the left side, which is good because I don't have a domain issue. If it was from the right side, I'd have a domain issue. So that's actually just 0, yeah? -2 times 0. And then we plug in, oh, nothing to plug in over there. It's just 3 minus 0 to den. So it's just the square root of 3, right? So we get 2 root 3 for that one. And I got one more where there's an asymptote in the middle, which is a little bit trickier. If you think that's enough, you can stop watching. This one will be a little bit trickier. Whoops, no limit yet. Sorry, we're just going to integrate from 0 to 4 of 1 over x minus 3 squared. Now, we're in this chapter of improper integrals, so it's really obvious that you should be looking for asymptotes. When AP exam comes along or final exam gets a little trickier because your mind's not saying indefinite integral or improper integral. We just want to just find that integral without thinking about it. So notice there's an asymptoted 3 in this problem, right? 3 minus 3 is 0. So what we're going to do is we're going to break this up into 2 different problems. One from 0 to 3, and then one from 3 to 4, because that's where that asymptote is. And then we're going to plug in the t's and do some antiderivatives. So I'll go ahead and plug it in. Limit as t approaches 3 from the left in this case, right? Because we're between 0 and 3. And then we're going to go 0 to t of 1 over x minus 3 squared plus the limit. Treat these as 2 different problems just because they are. Maybe I should use a different variable, but I'm going to use the t again. 3 from the right, the integral from t to 4. Okay, I'm going to go ahead and do the integral now. It's going to be the same for both, which just looks bad because it looks like there's only one. This is just like a quick u sub, u equals x minus 3. So it's just u to the negative 2. So think about this is just u to the negative 2, which would be u to the negative 1 over negative 1, right? So how about negative 1 over u, or in this case, negative 1 over x minus 3. So that's my antiderivative. So we do this left side first. Negative 1 over x minus 3. And we're going from 0 to t, and then we're going to add that to the limit as t approaches 3 from the right. Whoops, I don't need that. I've already done the integral of negative 1 over x minus 3, and we're going on this one from t to 4. So be careful here. Now, as we go from the left, well, I'll plug it in, I guess. Negative 1 over t minus 3 minus negative 1 over 0 minus 3. I'll just kind of just go down this side for right now, and then I'll go back to the other side. Limit as t approaches 3 from the left. So now that's going to be 3 minus 3. It's going to be 0, but remember, the answer to this is either going to be negative infinity or positive infinity. So 3 is from the left, so it's smaller than 3. So a number smaller than 3 minus 3 is going to give you a negative number. But then the negative sign in front of that problem is going to make it positive infinity. So that's going to be infinity plus negative 1/3. All right, and now over here, limit as t approaches 3 from the right, negative 1 over 4 minus 3 minus negative 1 over t minus 3. So now the first term is negative 1. Now we plug in that 3. It's bigger than 3. So 3 minus 3 is 0, but it's just approaching that. So it's approaching infinity. And then we got plus, so plus infinity. And we're going to add these 2 things together. So notice we got a lot of infinities right here. Infinity, or we could use that word diverges. Sometimes you might get infinity minus infinity, which technically we should use L'Hopital's rule for, but I can tell you on all these problems, the infinity minus infinities will be 0 because what's happening is you have these, like in this case, there's an asymptote at 3, right? So maybe it goes like this. In this case, maybe they're both above the x-axis. That's why it was positive infinity. But if one happens to be above and one happens to be below, this would be negative infinity. This would be positive infinity. But they're approaching at the same rate, which means that infinity minus infinity is going to be 0. So have fun with these improper integrals. We'll go over them in class tomorrow.